Hello, I am Muhammad Ribul Islam. I am from Bangladesh. Currently, I am working as a research assistant in SL Lab under supervision of Professor Jayang Park. Uh, Now, I am studying on fourth semester, Department of Electronic Engineering at Kangwon University, Seoul, South Korea. My research interest in energy harvesting using triboelectric nanogenerator technology for cell power sensor. Today I like to review of indium gallium phosphide or gallium arsenide HBT foundry. Now I am discuss a block diagram of foundry service process as shown figure 2.1. Through this curriculum, the overall MMIC layout and fabrication process are shown. In foundry service process, customer use the MPW application, that means multi-project wafer, which describes sharing of wafer and it's explained in next chapter. Before fabrication, the company request a NDA, that means non-disclosure agreement submission. Signing of this agreement means that customer can never abuse its content. The RSR regular shuttle run is then verified. After being informed of the due date, the offer design kit is received from the company. Here the HBT process I want to discuss. The HBT process can be separated in two parts for explanation. One part is concerned with the transistor aspect. The other parts includes the rest of MMIC and its backside. Hey, here as shown on the top basic wafer, the 6-inch indium gallium phosphide HBT process progress are shown in figure 2.2. The HBT EPI structure: first indium gallium arsenide or gallium arsenide emitter gap, gallium arsenide collector, gallium arsenide subcollector, and Si gallium arsenide. In figure 2.3, font size flowchart. First, each part is pattern. The order is follow: first emitter contact, then emitter isolation, then first base pedestal, then base contact, and then goes to second nitrate, and then first base pedestal and second base pedestal. After that we will go collect contact, mesa isolation, third nitrite, nickel chromium resistor, and then first nitrate via interconnected metal sheet and interconnected metal. Then we will go fourth nitride, second nitrate via air bridge post and air bridge metal. And second part, evaporation, lift off, etching and deposition follow, with each step processing the process. In some case an individual layer can be added or removed for specific application. And third, the final passivation nitrate via FPS and final passivation process remain. Here this one the front side 6-inch HBT process, and the backside flowchart is pair wafer bonding, then backside via. Then here in backside via include wafer thinning, backside via photo, and backside via etch. In metallization process include backside scribe state, backside photo, and backside state gold etch. And another spare wafer demount and scribe and break. And here I want to discuss types of process and their merits. Three types of process are detailed in table 2.1. First, three process like high power, that means HP process, high linearity HL process, high speed HS process. In case of ASP process, in practical application, PA of GSM, DCS and base station, and here discuss characterization is DC gain equal 87 and HL high linearity process use practical application of PA of WCDMA and WLAN and its DC gain 110 and high speed by HS process practical application in TIA laser driver high speed digital circuit and WLAN and its DC gain is more than HPHL 130. Now I want to discuss about active devices. Active devices must have the characteristics of amplification and non-linearity. It requires DC bias such as TR and diode, and 3V HBTs have a heterogeneous structure, high electron mobility and velocity. Here question, why electron mobility and velocity is more good? Due to heterostructure that takes advantage of its superior transfer properties, and HBs are based on substrate of gallium arsenide material with high resistivity. Heterojunction which process a band gap difference between the emitter and base, which a higher emitter injection efficiency and higher current gain than the homojunction. To increase the electron mobility, a very high base dropping concentration and very base thickness are achieved by epitaxial growth. Here we can see a cross-sectional view of indium gallium phosphide or gallium arsenide HBT structure. Therefore, in case of a high linear process, active device is so named because of its intrinsic device linearity of indium gallium phosphide HBT, uniform current characteristic, gain characteristics are function of collector current, independent collector capacitance, and high early voltage. Now now here discuss modeling. For perfect modeling, we need required some parameters like parasitic, intrinsic, DC, and AC parameters. Here you can see 2.11 the modeling measurement setup, which from Kangon University. First, measurement software and measurement hardware. That time we need to fix some parameters like parasitic, intrinsic, DC, and AC parameters. HBT device parameter. The modeling device reported in this work is based on 6-inch indium gallium phosphide and gallium or gallium arsenide HBT device technology, which utilizes 1 emitter finger with width of 3 micrometer and an emitter length 20 micrometer. The measured HBT DC current gain is approximately 112 at a current density of JC 25 kiloampere per centimeter square. The breakdown voltage BVCO and BVCBO are 12 and 23 respectively, which are suitable for most IC application. The 3 into 20 micrometer to single emitter HBT achieve peak FT and Fmax of 50 GHz and 85 GHz respectively. VBIC model. Now I want to discuss about VBIC model. Here we can see an equivalent circuit of VBIC model. VBIC model was developed as an industry standard replacement for the SPICE Gummel-Pon, that's called SGP model. VBIC model was intended to improve deficiency in the SPG model that have become apparent over time because of the advances in BGT process technology. However, 45 includes improved modeling of early effect, cohesive saturation, substrate and oxide parasitic, valence multiplication, and temperature behavior, all of which can be invoked selectively based on particle model parameters value. The basic equivalent circuit of VBIC model is shown in 2.12. Extraction of parasitic elements. Here now discuss about the parasitic capacitance. First of all, here you can see the HBT T model, small signal equivalent circuit. The HBT model, small signal equivalent circuit, has observed the parasitic capacitance in the input and output to the ground are CP1 and CP2 respectively. The parasitic capacitance are extracted by open patterning. In case of parasitic capacitance, it's the characterization of AC behavior of microwave transistor. Usually a set of two-port S parameters is measured using scalar network analyzer. When the performing high frequency measurement on wafer, a correction procedure must be followed. That is, the on wafer parasitic must be characterized so that from the measurement the actual transistor two-port parameters can be obtained. And here also we can see the photograph and equivalent circuit of open pattern. From the equation 2.2.5 and 2.2.6, we mainly the value of capacitance is determined by the average of capacitance in the flat frequency region. The CP1 45.84 femtofarad and CP2 its value 72.39 femtofarad. And here the parasitic inductance of extraction of parasitic elements. Here mainly the parasitic inductance are extracted by short patterns. The here mainly LE, LB and LC indicate the parasitic inductance in figure 2.13 and 2.17. From the figure 2.2, 2.2.7, 2.28 and 2.29, we got the inductance like LE equal to mainly 20.22 PAs and LB 55.92 PAs and LC equal to 55.31 PAs. Here overlap capacitance, extraction of parasitic elements. This one the fitting of the sum CBC and CBCO function for junction capacitance. The bus collector overlap capacitance CBCO is explained in this part. The capacitive coupling due to the geometric overlapping between the base and collector in the HBT can give rise to charge feed through. The exact value of the base collector overlap capacitance is determined by the measuring the S parameters of HBT with 0 voltage applied the base emitter junction. And from the equation 2.210, the overlap capacitance is obtained as 33.82 femtofarad. At the extraction of intrinsic elements like resistance, the intrinsic S parameter is converted and obtained in the above de-embedding process. The next whole extraction of parameters are carried out using intrinsic S parameter. The base collector junction capacitance CBC and the base emitter junction capacitance CVE are increased by applying 0 voltage into both collector and the emitter and by simultaneously applying high current into the base. Therefore, the base collector impedance JBC and base emitter impedance JBE can be neglected. Consequently, the values of resistance of emitter, resistance of base and resistance of collector are 1.43 ohm, 1.17 ohm and 1.14 ohm respectively. Here the extraction of DC model parameters like IV characteristics curve. Figure 2.27 has shown the IV characteristics under constant current drive of the HBT, and 2.28 the IV characteristics under constant voltage drive of HBT. There are two types of IV characteristics curve. One applies current to the base and another applies voltage to the base. This IV characteristics curve is necessary to use IV curve with constant current and another IV curve with constant voltage. The parameters such as XIN and XII and XIS are associated with IV curves under constant current and voltage simultaneously. Hence, it is important to extract suitable parameters simultaneously. Figure 2.27 and 2.28 show a comparison simulation and associate measurement depth of IV characteristics curve. The another extraction of AC model parameters, junction capacitance. The junction capacitance are some of the most important electrical parameters for characterizing bipolar transistor BJT. They play a significant role in the switching speed and the frequency response of bipolar transistor. In the base collector capacitance is very important in determining the AC performance of bipolar transistor. The extraction method for the base collector junction capacitance is called CBC, and base emitter junction capacitance CBE are shown in equation 2.238 and 2.239. And here as shown figure 2.29, verification of junction capacitance curve with one is measurement value, another is simulation value. Here transit time parameters, extraction of AC model parameters. There are four types of parameters with respect to the transit time in VBIC model. One TF, XTF, ITF and BTF. The S parameters modeling results from the parameters of junction with transit time parameters as shown figure 2.30. In case of passive device, in MMIC device, passive device used for impedance matching, DC biasing, phase shifting, filtering and many others. For transmission line, the microstrip is a flat strip of conductive material separate from single ground plane by dielectric material substrate such as gallium arsenide. With microstrip line, the dielectric constant must be replaced with the strong dielectric constant. Here discuss MMI capacitor, spiral inductor, resistor and via hole and plate. First of all, discuss about MIM capacitor. Both overlay capacitor and interdigited capacitor can be used in MMIC. Interdigital capacitor can be used for values up to approximately 1 picofarad above which their size and resulting distributed effect prevent their use. The most popular type of capacitor has become the metal insulator metal capacitor, which shown in figure 2.32. That's reference plane of an MIM capacitor device. Therefore, smaller and less costly circuits are possible. DC blocks massing section, uh, biasing uh, biasing circuitry are widely utilizing these components. This thin film capacitor is composed of two metal plates separated by dielectric materials layer. Typically, the dielectric layer overlaps the first metal equal to IMS and IM layer, and the second metal equal to ABP and ABM has a smaller area than the lower metal layer. The area of air bridge post determine the capacitance value, but produced by the K company has capacitance value of 0.4 to 30 picofarad. This physical structure helps minimize the fingering fields to ground and shorts between the top layer metal layers. This air bridge is often included to further minimize the parasitic capacitance. Because the dielectric layer is substantially thinner than the substrate thickness, metal insulator metal capacitor exhibits significant fingering effect. Now, spiral inductor. Due to its high Q quality, the spiral inductor has become popular, and it's shown in figure 2.33, the reference plane of spiral uh, inductor. The inductance value of this spiral inductor provided by K Kong is 0.28 to 24 nano H. Additionally, they provide two types of square spiral inductor. One of these types shown in another figure. Structure of entire air bridge and air bridge post equal to EA type. In this case, the size of air bridge post in 1 micrometer is smaller than that of air bridge microstep line. Another thing is resistor. The resistor in an MMIC can use doped semiconductor layer of deposited thin film resistive layer. In this case, the material of resistor is a nickel chromium thin film. Sputtered thin film resistor offer improved linearity and lower temperature coefficient in comparison to that of other. Additionally, sheet resistance of 50 ampere square can be produced, which is convenient for the circuit designer. Another thing is via hole and pad. The backside via holes are used to connect the device or RF radio frequency circuit on front side, and metallized back inside for grounding and thermal dissipation. Substrate via holes is available for 95 micrometer plus minus 10% thickness of gallium arsenide wafer. Via holes may be modeled in RF device as a single port from the front via pad to the back end side ground. The configuration and physical parameters of via are given in the following 2.7 figure, the via configuration. The layout design rule, the general consideration, mainly the maximum stepping tile size on the wafer. The stepping tile size generally is the first thing that must be considered. In MPW process, the wafer is shared, which is why the size of resulting chip is limited. Additionally, the chip shape is perfect square. As a result of this process, the maximum width and height of chips are both restricted to 15 millimeter. And another thing, the transistor orientation. The figure 2.3 in the wafer configuration. From the same reason, at first consideration, the emitter direction must be a common parameter. This is shown 2.3, the wafer configuration. On bottom of the wafer, a groove is hollowed to establish up established up from down. Additionally, there are alternatively way to denote the downside on wafer. The prototype MPW 16 marks layout. MPW is abbreviation from the term multi-project wafer. As mentioned previously, user may share the wafer during the manufacturing process. This is because it's too expensive to use whole wafer and individual wafer is frequently too large for one project. Hence, each user shared the wafer. Each customer uses the given rules in designing and desired circuit. After that, the company gathers each circuit and fabricate on the on one wafer. The term MPW comes out of this process. Next, the GDSII stream file format and standard cell. When the layout database is submitted, it should be in GDSII file format. GDSII stream files must have default GDSII units. This format uses the standard cell library that K company supplies. These files are also the used to unify and interset of chips on wafer. Here shows the various pattern of accurate angle corners. And layout design rule types. There are mainly 6 types of simple layout design rules are described this table, like width, length, spacing, extension, overlapping, surrounding. This width means the shorter dimension of all object in any direction on the named layer. Length, the longer dimension perpendicular to the width on named layer. The distance that separating all pairs of objects either on the same layer or between the two different layers. Spacing. Extension, the amount that an object on one layer must extend beyond the edge of an object and another layer. Overlapping, the amount that an object on one layer must overlap an object on another layer. Surrounding, the degree to which an object on one layer must completely surrounded by object another layer. Here another thing, figure 2.43, an illustration of layout design rules like width, length, spacing of layer 1 to layer 2, extension of layer 2 to 1, overlapping of layer 1 and layer 2, surrounding of layer 1 by 2. And another thing here, mainly the layout design rules, design mainly DRC main abbreviation of design rule check. uh, that is important for engineer to check all or part of the design, confirm whether it meets manufacturing specification. There are 2 types of DRC. One is quick check, mainly it pertains to the minimum width and spacing, so basic design are required. The other thing, the custom check, which is carried out according to a pre-written set rules. And this DRC procedure is given below. Define or select design rule, then run the design using defined or selected rule, load the results and view any error that we found. Here mainly I discuss and explain about the indium gallium phosphide or gallium arsenide HBT foundry in shortly. And thank you all to watch these topics. Thank you all again.